Alright, let's start by talking about two terms that often come up when we deal with AI models: explainable AI or XAI and interpretable AI or IAI. At first glance, they sound very similar, but they actually refer to the slightly different approaches. Explainable AI is about taking a complex model, maybe one that's already been trained, and then trying to make sense of its decisions afterwards. And think of tools like shape values, line, or attention maps. These are techniques we use after the model gives a prediction to say, here's why the model probably made that choice. Okay, and interpretable AI, on the other hand, is about using models that are transparent by design. A linear regression or a small decision tree falls in this category. When you look at them, you can directly see how the input affects the output without needing an extra explanation method. And now, why do we even care about interpretability or explainability? Well, one reason is trust. If users or stakeholders don't understand why a model is making certain predictions, they will be less likely to rely on it. There is also regulation in some industries, finance and healthcare, for example, where you can't just use a black box model and say, trust me. You need to be able to explain decisions. And then there's bias detection. If you can't interpret or explain what the model is doing, you won't catch if it's unfairly treating one group differently. And lastly, explanations often help us improve the model itself by pointing out weaknesses or errors. And of course, nothing comes for free. One of the biggest challenges here is the trade-off between accuracy and interpretability. Generally, the more complex the model, the higher the accuracy you can potentially achieve, but the harder it becomes to understand. A linear model is easy to explain but might not capture complex relationships. A deep neural network might predict very well, but good luck explaining every decision it makes in a straightforward way. On top of that, explanations themselves can get complicated. Sometimes the explanation method is harder to understand than the model output, and then there's a cost, extra computation, extra time to generate explanations. Okay, and where does this really matter? In areas like healthcare diagnosis, we need models that doctors can understand and justify. In criminal justice, if an algorithm helps decide parole or sentencing, you can't just accept a number from a black box. You need reasoning. And the same goes for financial services like credit scoring, where regulators demand transparency. And in autonomous vehicle, if a car makes a wrong turn, engineers must be able to trace why it happened. These are all what we call high stakes domains where explanations are not a nice to have, they are essential. And here let me give you a spectrum to think about. On one end, we have interpretable models, linear regression, decision trees, where the reasoning is clear and direct. In the middle, you have semi-interpretable approaches like ensembles. Random forests, for instance, are harder to interpret than a single tree, but not completely opaque. And then, on the far end, you have deep learning systems, which are often treated as black boxes. These provide excellent accuracy, but are very difficult to explain in a human-friendly way. The key question is, given your problem, where should you be on this spectrum? Okay, and Let's continue. Okay, now let's take a look at the black box problem with a simple demonstration. You will see here, and let's say you have three features A, B, and C. If we use a linear model, we can assign weights to each feature, and when you change the sliders, the contributions just add up in a predictable way. Okay, and in example shown, the model predictions come out to about 54.2% probability, and you can see clearly how feature added to the result. But if you switch to the black box here with the exact same input values, the prediction might drop to 27.8%. Why? Because in black box models, the interactions between features are not simply additive. They are nonlinear, and sometimes they involve complex relationships that are not obvious at all. Okay, and this becomes even clearer when we visualize the contributions. And in the linear model, each feature has a straightforward contribution. You can say A contributes this much, B contributes that much. But in a black box, the contributions are messy. Feature A might interact with C in a nonlinear way, and suddenly their combined effect is very different than just adding them up. This is why attribution in black box models is so challenging. Okay, and that leads us to an important point. Accuracy alone is not enough. If you can't provide a clear, defensible explanation, the model might not be suitable for real-world use. And here you can see as interactively. Okay, and let's do it for B. And for C, and here look at C, and let's make it for B. Look, it is negative. Okay, and we can do it for A, and linear is here, and be careful. Okay, and let's make it for A again, like that. Okay, I think that's okay for you. And let's continue. Okay, so then how do we decide which approach to use? Well, it depends on factors like risk level, the need for transparency, and latency requirements. If the decisions are high risk and transparency is critical and you need fast results, then interpretable models like logistic regression, scorecards, or small decision trees are often recommended. Okay, and if the risk is lower but transparency is still needed, you might go for semi-interpretable options like GAMs, small random forests, or shallow neural networks. And if transparency is less important and accuracy is the main priority, then explainable black box models like post hoc explanation methods might be acceptable. And the point is, model selection is not just about squeezing out the highest accuracy number. It's about matching the model to the context in which it's going to be used. Okay, and I hope that's okay. And let's look at this part. So what's happening here? You can see our risk level, transparency need, latency budget, and low risk. You can see recommended approach. And medium risk, nothing changed. High risk, and transparency needed, performance and high transparency, and latency budget, low, and medium risk, you can see, and high risk, that's here. Okay, let's continue with these new parts and build on what we have been discussing. So okay, here we are looking at an interactive comparison between models, and the main topic is the trade-off between accuracy and interpretability. On the plot, each point represents a model. Okay, the vertical axis is accuracy while the horizontal axis is interpretability. And you can see that as we move to the right, interpretability increases, but in many cases the accuracy starts to drop. That's the classic tension. A highly interpretable model might not be the best at capturing complex relationships in the data, while a very accurate black box model might give us little understanding of how decisions are being made. And look at here, take the example of logistic regression, which shows about 70.1% accuracy. That's not the highest accuracy on the chart, but notice that its interpretability is very high, 95%. And that's because linear coefficients in logistic regression directly tell us how features affect the prediction. If the coefficient for income is positive, then higher income increases the predicted probability of the positive outcome. And that kind of clarity makes logistic regression inherently interpretable. Okay, and here, if we drill down into the logistic regression details, we can look at both accuracy and interpretability scores side by side. Okay, and here so let's look at random forest, for example. Accuracy higher but lower interpretability. Look at this point. Now it is red, and gradient boosting, did you see? And let's look at deep neural networks. Accuracy is higher while interpretability is very low. And what's next? Decision trees. Here interpretability is very high, and support vector machine is here. I think that's okay for you. And let's shift to another important aspect: bias detection and fairness. Here we are monitoring performance across different demographic groups. On the chart you see three groups: A, B, C, and notice the gap. Group A has higher accuracy, precision, recall, and F1 score compared to groups B and C. Group C in particular is underperforming significantly. What does that mean? It means the model is not treating all groups equally, and that can indicate bias. So, if we quantify the disparities, we see accuracy disparity at about 27.6%, precision disparity close to the 29%, recall disparity at 12.8%, and F1 score disparity at 28.6%. The average disparity comes out to 24.5%. And to put that into context, many organizations use 10% as a screening threshold. So here we are well above what would usually be considered acceptable. That's a warning sign. If deployed, this model could create unfair outcomes. So what can be done about it? There are several mitigation strategies. Okay, you can see here. And we can rebalance the training data or adjust sample weights so the model doesn't overfit to one group. Another option is to apply post-processing calibration separately for each group. We can also add fairness constraints during training so the model actively balances across groups. For borderline decisions, human review is another safeguard. And of course, once the model is in production, monitoring fairness continuously is key because bias can creep in as the data changes. Okay, that's done, and regenerate, you can see it changes. It's always changing. And real world applications here. So let me look. Okay. In healthcare, interpretable AI can support clinical decision making with transparent risk scores. And here we can see a physician can see exactly why the system is recommending a certain treatment, and regulators can audit the trail. In financial services, explainable AI helps with credit scoring by providing clear criteria. It also allows institutions to reject or flag uncertain cases with justification and to monitor fair lending practices. In supply chains, models can forecast demand, but crucially, they need to provide explanations when forecasts are overridden. Optimization planning benefits too when constraints are made explicit and traceable. And fraud detection is another area where explainability helps. Ensemble methods, when paired with sharp explanations, allow us to identify case-level risk factors and in human-in-the-loop workflows, and you can combine automated detection with human judgment. In HR and recruitment, interpretability ensures that candidate evaluations are transparent. Okay, and bias monitoring across groups prevents discriminatory patterns, and if an applicant is rejected, adverse action explanation letters can clearly state why. And in autonomous systems like self-driving cars, documentation of safety cases, scenario-based decision attribution, and fail-safe triggers all depend on transparency. You need to know why the system acted the way it did in any given situation. Okay, so to sum this batch of screens up, the big picture is that model interpretability is not just an academic exercise. It's deeply tied to fairness, safety, and compliance. From healthcare and finance to HR and autonomous vehicles, the choice between an interpretable model and a more complex explainable model has real consequences. And the right choice depends on the balance between risk, performance, and the level of explanation required.